So it's my honour actually to be talking here amongst some HPC legends. In my biography in the book, it's I think quite ironically says I've been with Mellanox since February 2013. So it's actually my second time around, so that's not quite true. So as part of this, I guess, sponsor session, what I want to do is just provide some highlights of what's happening inside Mellanox, inside HPC, and that includes InfiniBand, VPI, and Ethernet technologies that we're trying to drive forward. Obviously, InfiniBand is a key part of what we're talking about here amongst the HPC community, and want to see how we're trying to just improve performance of that and drive that further on forward. So for anybody that doesn't know, I guess most people know Mellanox around here, so we're a technology-driven company, and the company's grown hugely into quite a large-sized company over the last couple of years. This picture is a picture of our headquarters in Israel. And the reason we've tried to drive standards and technology. So we've come to market with 56 gigabits FDR InfiniBand. We have a very solid roadmap to EDR and beyond. We're driving also 1040 and also 56 gigabit Ethernet as well, and have a roadmap to 100 gigabit Ethernet. And the company executes, which I think is why we're successful. Certainly, when I had my sabbatical away from Mellanox, looking in from the outside, that's one of the things that you see. And so the top 3 points here, I guess, talk to what we offer as a value proposition. So we drive technology to bring the best performance, the lowest power, and hopefully at the lowest cost possible to bring the greatest value to deployments and help to drive towards exascale and other initiatives, including GPU clusters. So we're a very sound company. We have good cash reserves and good flow. Approximately 60 to 70% of our employees are engineers and R&D. So a big technology company. And this is what we do with all of our engineers. So a big USP that we have is that we're pretty much the only vendor around which does everything end-to-end, which includes very low, from the very base of a design, so producing our own silicon ASICs and ICs. So with those ICs, we have the ICs for the HCAs and NIC cards, also for the switching solutions that we provide. So we don't need to rely on anybody else externally, which gives us a great deal of control over our environment. So you see here on this, just spend a couple of minutes on this end-to-end diagram. So obviously having high-performing technology on the adapters and in the switches is great. You need to have that to complete a fast network. But in between as well, we need to make sure that interconnect is performing as well as possible. So we have very strict testing guidelines that we work to internally, and we actually make sure that we're pushing the boundaries of cable quality and technology to the point where if there is a manufacturing error which is further down the pipe, we'll help to correct that as well. So the same families can be used for Ethernet between 1 to 56 gigabit Ethernet, and InfiniBand, all brands from SDR up to FDR currently, and also moving forward with EDR. And then on top of that, we have running the Mellanox OS and UFM. So Mellanox OS will obviously provide the base OS on all of the technology end-to-end as well, so you can control the switches and the HCAs. And on top of that, we have a package called UFM, the Unified Fabric Management Software, which helps you to really dive down deep into the solution and check what's happening literally on a channel basis, and inspect where any packets may be doing something which you didn't anticipate. On top of that, we have a number of accelerators that we have. So I'm going to talk about some of them a little bit later. So some accelerators to improve message rates, to improve collective offloads in a fabric, some based around storage, and then something else so we're driving accelerators, and we're very keen to promote open standards as well. So I mentioned that we have Ethernet and InfiniBand technology. So we call that virtual protocol interconnect. And I guess the utopia that we see is that everybody has their own opinions and does their own work to establish what is best for them, what's the best interconnect for their particular application or their cluster or their network. So our utopia is that we don't care if it's InfiniBand or Ethernet. And so to that end, we have our VPI technology, which goes, again, end-to-end, so across the adapters, also across the switches. So looking at the adapter, we have the ConnectX family, which started off with an SDR family. We now have ConnectX3, which is both an Ethernet and InfiniBand adapter technology. So we actually have this running now with back-end PCI 3 by 8 and by 16 interface. And this silicon goes onto our own adapter cards and also onto motherboard designs as a LOM design, or mezzanine cards through many OEMs that we work with as well. And each of these adapter pieces of silicon in ConnectX3 can be used also for Ethernet or InfiniBand. And running on top of that, we have the networking, message accelerators, the storage and clustering accelerators again, and also traffic management accelerators running on top of that. And of course, looking at the wider ecosystem, that would be no good if we didn't support the likes of VMware and different Linux distributions. So we partnered with them. We partnered with all of these companies in the ecosystem. And I think that we can support a large number of virtual machines. In fact, a number of our press releases that we have with end users and with partners will talk about the amount of additional virtual machines that they've been able to implement in using our solution. And then just going across quickly to look at Switch X2, which is our Switch X Silicon, which is our switch silicon. So this also supports 64 ports of, I guess, small, lower data rates and up to 36 ports of higher data rates. And that can be 10 gigabit Ethernet, SDR, DDR, or FDR, 40 or 56 gigabit Ethernet. And all of these can mix and match. So inside a particular switch, you can have 8 VPI subnets, which means you can swap between InfiniBand or Ethernet or different subnets of each of those as you will. So that's really handy in an application where you may have a number of HPC clusters running InfiniBand and maybe with an Ethernet-based Metro campus. So ConnectIB is, there's a couple of figures on the next slide, but ConnectIB I think has been a big game changer for people who've deployed that. It's essentially, we have 2 ports of FDR running on the same card. The card, the ConnectX silicon, the ConnectIB silicon, has PCIe 3 by 16 interface coming off the back of it, so you can actually use that full bandwidth. You can use those 256 gigabit per second ports coming off and going into the client. So you can have hundreds of virtual machines on a client interface. And so you get really huge figures, things like 137 million messages per second, so huge message rates. And great, you can use all of that bandwidth. And so it really is a step towards exascale. There's been discussion of exascale for a number of years now, and we think this is really a step towards that. So some of those figures here. So you can see you can see full bandwidth of both ports being achieved on the left here. So there's 256 gigabit per second ports running, and they're being offloaded onto the PCIe 3 interface, achieving 137 million messages per second. So if you compare that to other InfiniBand solutions, previous QDR solutions, that's really about 4 times the rate that you could see previously. And then the number of million messages per second, in recent tests, we've seen 137 million messages per second, so huge data rates. So just coming back to what I was talking about the virtual protocol interconnect. So the way this started inside the product offerings that we have is we have InfiniBand switches, we have Ethernet switches, and never the two shall meet. The world might implode if those two come together. So as what we have now, what we have on currently is VPI Bridging, which is the 8 VPI subnets that I was talking about. So what you can do is you can, what's shown here is 1036, which is a 36-port switch with QSFP interfaces. So that can be running QDR, FDR, 40 gigabit Ethernet, or 56 gigabit Ethernet. And so essentially you can have 8 subnets on that, and each of those subnets can bridge between each other. So you can run maybe Ethernet for throughput storage, InfiniBand going into a cluster. Really use that how you will. And then if we take a step forward for what we're going to introduce next on the same box. So this is all the same silicon, the same box, and it's really firmware upgrades that enable this. So then the next step for us is to take the same box and essentially switch any port to any port. So switching any Ethernet port to any InfiniBand port, and you can configure that box to be whatever you want it to be, however many ports of each, including 0 of each, if that's what you wish. So really, I think really merging two worlds here, really merging a network and cluster technologies. So right at the beginning, I spoke about the value proposition that we have is offering great performance, low power, and a great value. So it's all very well to say that and to put up a load of slides that we may have done ourselves to show what performance we receive. So this is all these figures come from the Tolley report. I'm sure you all know Tolley. So essentially, they've taken one of our switches into the lab and basically run the switch, connecting up every port and running at full line rate across every port to see what results they get, to see if what we say in our data sheet is correct. And I think what's important here is that we can run at wire speed, full line rate on every port at every packet size. So everything from below 64 bytes to jumbo size packets with absolutely no losses at all, no drops, which is fairly unusual. You see I guess in other technologies, what you'll see is when you get down to 64-byte packets, then it's difficult to handle that data flow through the switching when everything is running at full line rate. And equally with other architectures, what you may see is when the packet sizes start getting larger, then you'll see the latency changing a great deal and becoming a lot higher. So from a multicast point of view as well, so if we look at layer 2 multicast, so all of that is very jitter free. It all is multicast out on the egress ports all at the same time, and this is all with a very low power. Probably equally as important as latency and low power and throughput is the jitter. So the jitter shown in these figures at the bottom is exceptionally low, around about 200 nanoseconds. And the range of jitter that we show here, arguably you could say that was due to the tester. Most network testers will be plus or minus 10 or 20 nanoseconds. So you could argue that that's within tolerance. So this is all using SwitchX silicon, don't forget, which is what you are used to using in InfiniBand clusters as well. So coming on again to what we mentioned about using IB, and speeding InfiniBand up. So we have this concept called Scalable HPC, and what that essentially is we can drive the physical speeds and feeds. We can drive from QDR now to FDR. to give better performance, but also what we need to do is make the transmission of messages more efficient. So MXM is Mellanox messaging accelerator. So it kind of does what it says in the tin. So if we look at the send and receive or put get messages, it will accelerate those messages. MXM takes care of the memory allocation on the HCAs, and also if you've got intranode communication, it will make sure that the memory is allocated efficiently for those operations as well. So essentially what it does is for all parallel communication paths, it makes sure that there's no bottlenecks inside those parallel communication paths, and that all of the put get and the receive messages are all pipelined and accelerated. FCA is the Fabric Collectives Accelerator. Sorry, tripping over my tongue. Used in MPI and PGAS. So again, what that does is it takes the collectives, takes the collective offloads, and accelerates those through the fabric. So it will set up a separate path through the fabric to normal traffic, which isn't subject to collective offloads. And that uses Core Direct technology, which is in Mellanox silicon end-to-end. So you can't do this without Core Direct. And essentially what we're doing is using the hardware facilities to accelerate collective offloads across the whole system. So Scalable HPC uses both of these, uses MXM and FCA accelerators to apply essentially what's described in OpenHPC. So essentially using accelerators to make sure that the end-to-end InfiniBand system is being used and the shared memory is being used correctly to gain the best possible performance and scalability. So looking at another topic, so this is all slightly piecemeal, but what we wanted to do is just try and highlight the things which we have going on, rather than just go through a product roadmap or something. So MetroX, we're pretty excited about. So as campuses grow, and as we're getting to exascale and people having to use data centers or warehouses which might be next to each other, or machine rooms which might be slightly apart. So we've seen the requirement for something like MetroX, which is essentially long-haul RDMA, and we can operate this over InfiniBand or over Ethernet. And essentially what we do is take a number of switch ports, put them over RDMA over deep fiber, and take them across to another piece of campus. So there are three products that we've brought out for this. One is kind of a shorter long haul, if you will. So has a larger number of ports, doesn't transmit quite as far. But if you have a couple of data centers or machine rooms which are next to each other, then you're going to be able to go between different machines or different clusters using this technology. And then as we progress through, there's a couple of other switches, one with a 10-kilometer range and another one with a 100-kilometer range, which has less less ports. So I guess the 100-kilometer product that would you would use that for backups or for resilience or for disaster recovery, I guess, more than the product with more ports. But I guess the important point here is there were a couple of solutions on the market previously, but what people had, if you needed to collect a large number of connections between data centers, then essentially you've got to start looking at really expensive WDM stuff, or other solutions which are going to blow the budget. So this is a way of maintaining a budget and spending that budget on servers or other things which are going to serve a good purpose. And I think there's probably been a bit of this highlighted during the rest of the other couple of days. So this is, some actual real-world examples of some of the things that we've been talking about. So reducing cost of application is a primary driver for us. So these are all InfiniBand examples that we've rolled out, that we've press released. So there's a couple of local ones here. Profit Bricks also talked about the number of VMs that they were able to implement, so 3 times the number of VMs that they had from the previous architecture, using the Connect X3 based HCAs and the Mellanox end-to-end architecture. And then there's some phenomenal figures here about the application performance and the increase in application performance as opposed to previous architectures that have been used. So the Oracle Cloud improved by 10x, Atlantic.net, 700% higher network performance. So just lowering cost of the network and the applications running on them, and just increasing the performance massively. And these are all cloud examples. Equally, you could look at these and apply them to hosting and Web 2.0 as well, or in fact HPC clusters. And then the value for money part. So we talked about increasing performance and the number of VMs, etc. So here, return on investment. So these are actual examples from customers and customer feedback that have been given. So one example that we have, which is a very large company, a Fortune 100 company. So they reduced the database recovery time from 7 days to 4 hours when they implemented Mellanox InfiniBand architecture. There's a Hadoop example here on the right-hand side. So essentially, when as data analytics becomes more important in the commercial world and in Web 2.0, then the faster you can process the data analytics, then the more money you can make in that world. And so it's obviously crucial to them to have the best possible solution. And then one thing I didn't talk about too much is the storage world as well. Storage is a huge driver, and the entry into storage can potentially be a bottleneck coming out of clusters or networks. So we work with a large number of storage vendors and have our products embedded within their solutions. And so we're helping to drive the performance there and reduce the cost of ownership, and also the amount of initial spend as well when storage is being implemented. So we continue to work with those partners to drive that performance and lower those costs even further. And then the other really exciting announcement that we had recently is around our Open Ethernet initiative. So in the Ethernet world, there's Ethernet is a standard. Everybody should do it the same way. But the reality is that vendors have their own proprietary management mechanisms, and so everything's a little bit different. You can get tied into greater or lesser extents into a single vendor. If we look at some of the larger vendors, and they have huge licensing fees and service contracts. So what Mellanox is doing as a strategic initiative, and it opening up to this community, and gladly will take any input from this community, is really driving the Open Ethernet initiative. So it's based on, if we look at OpenFlow, a number of vendors have started to release OpenFlow and SDN products. Essentially, the feedback we've had is that when you look deeply into that, it's really a slim API that is offered from other people, and they don't really want end users getting too deeply into their hardware and into their products. So we're going to try and what we're trying to do is essentially blow that out the water. So if we look at why OpenFlow came about as a concept originally, there's a great paper actually written by Nick McEwen in 2008 of Stanford, and he talks about the need for OpenFlow to allow campus networks to experiment and try different routing protocols, and that's not possible on production traffic on switches which are what he calls vendor locked, because nobody wants the traffic taken down, the network taken down by experimental traffic. So essentially OpenFlow as a concept started to allow that to happen, to allow people on campuses to experiment with different networking algorithms, something that may be more efficient. But that's had a very slow slow way to life. So we've come up with this Open Ethernet initiative, and essentially OpenFlow has two really categories of switches. One is an OpenFlow enabled switch, and another one is an OpenFlow switch, a truly OpenFlow switch. So we're working with open source organizations already, and so what we want to do is completely open it up. So we'll still continue to provide our own form of Ethernet switching, and in fact VPI switching. So if you have an Ethernet switch from us, you can also use it for InfiniBand if you need to reprovision it somewhere. But also what we're going to offer in a parallel path into the open community is an open flow switch. So you will be able to go on that, have OpenOS, have open switching and L3 routing protocols on there. So Quagga is one which is gaining in popularity, and run an open management source code on there as well, and really drive the industry towards open flow that way. Why are we doing it? Well, open is good. We're a technology company, and we execute, and we deliver well according to new standards. So for us, opening this up and stopping customers and end users being locked down into solutions which are not ideal for them is a good thing for us. We like open source. So we're real excited about that as an initiative. And I believe that was everything that I had to talk about.